Let us do the proof of unbiasedness of an OLS estimator. So you start with this. You say that you have the model yi equals to beta 1 plus beta 2 xi plus ui, right? Guys, this is the non-random part, not changing. Non-random part. So even though beta 1 and beta 2 are unknown, but they are fixed, right? They are fixed constants, right? This guy is a random part or a random component. Okay. You run the regression, and once the moment you run the regression, you get this expression. So yi hat is equal to b1 plus b2 xi. This is what you get. B1 and B2 are the OLS estimates which you have. And from the earlier recordings, you know that slope estimator is this summation of small xi yi upon summation of small xi square, right? Small xi and small yi, they are the deviations from mean. So small xi is capital Xi minus x bar, capital Xi minus capital X bar, and small y is capital Y minus capital Y bar. Mhm. Minus this guy. So you guys could see very easily that this B2, this is dependent upon Y, right? Y is dependent upon UI. UI is random. So this B2 also has a random component. It has a fixed component in terms of x's, but since it is dependent upon y and y is dependent upon both random and non-random, so b2 is also dependent upon the random component, right? So let me just write your uh, numerator for this first. So it is what? Summation of xi minus x bar. In place of yi, you guys can write what? Beta 1, your true model, plus beta 2 xi plus ui minus, in place of y bar, what will you write? Beta 1 plus beta 2 x bar plus u bar, right? You guys can write this beta 1 will get cancelled out. And this will be beta 2 capital Xi minus capital X bar plus ui minus u bar. Fair enough. So you have basically beta 2 will come out of the summation sign, and it being a constant, and this is xi minus x bar square. So now when I say x, I mean capital X only, right? So here I want to differentiate between small xi and capital Xi, but now until the end of the lecture, in case if I say xi or y, it means capital Xi, capital Y. Ui minus u bar. Fair enough. Okay. So what is your B2 will look like? Beta 2 summation of xi minus x bar ka square plus summation of xi minus x bar ui minus u bar minus this. So this is just what, b2, sorry, beta 2. Hmm. Oh, sorry. Da, da, da. Right. Hold upon. Avata. Huh. So it is dependent upon beta 2, which is fixed. That's a fixed component. And it is also dependent upon this u, which is a random component. Okay, it is dependent upon u. Let me also write this x, this guy, numerator for this guy again, as what? Minus u bar, right? Beta, this is sum of deviations from mean, na? That is equal to 0. These are sum of deviations from mean. That is equal to 0. These are sum of deviations from mean. They are equal to 0. Your numerator can be just simply written as summation of xi minus x bar ui. So again, write your b2. Oh, this is an important proof, right? I mean, you need to know for your exam. And by the way, the uh, reference for this is Christopher chapter 2, right? This is, I think, this is there in your reading. I can write like this. Can I write it like this? Write like this. Mhm. And this I'm calling it as A, the thing in the parenthesis. This I'm calling it as A. This A is nothing but the linear combination of the values of the disturbance term, right? So linear combination of the values. So with the disturbance term in all the observations in the sample. Fair enough. So this AI is this beta. It is this xi minus x bar upon summation of xi minus x bar of RAM, right? So you need to understand one thing. When I write I here, and it should be rather written like this. When I write I here in the numerator, so as your I is changing, your numerator is also changing. As your I is changing, your numerator is also changing. X1 minus x bar, x2 minus x bar, and so on and so forth, like that. Here, this denominator is basically the square of the deviations, and it is for the entire sample. So this is not going to change. So the numerator You can write changes as I changes. Mhm. And is different for each observation, right? So denominator as such is not dependent upon I, because this is what, in case if you, even if you write I starting from 1 to n, so it is what, your x1 minus x bar ka square plus x2 minus x bar ka square and so on to xn minus x bar ka square. So in a way it is not dependent upon I. The denominator is the sum of squared deviations, is the sum of squared deviations for the whole sample, and is not dependent upon I, right? So Dougherty says, I mean, instead of writing your, I mean, although there is I here also, but you can also write this as J because this is not dependent upon I, it doesn't matter. So he says this, that we will rather write the denominator of AI as this guy, just to have no confusion at all. Doesn't matter. I mean, although I like the proof, the way it is given in basic econometrics Gujarati, but Dougherty is one of the reading in your course. You still have to use this in your exam. You will have to use this in your exam. But I hope this point is clear to you, beta. Let me write few things first. Mhm. Summation of AI is what? Summation of xi minus x bar upon summation of j starting from 1 to n xj minus x bar ka square, and it is, हाँ बेटा, so it is what? Beta, what is this? Sum of squared deviation, sum of deviations from mean na? So this is equal to 0. This is equal to 0. You with me, beta? Hmm? So there is a purpose we have written this as J. It doesn't make any difference. It is not as such dependent upon I. So whether you write I, J, till the point it is there in your head that it doesn't matter actually. Huh? Okay. Second point. What about this guy? Summation of AI square. Have it up. So it is what? It's like this. Now you understand one thing. When I write I equals to 1 to n, it will be what? x1 minus x bar ka square plus x2 minus x bar ka square and so on. So whether I write I starting from 1 to n or j starting from 1 to, how does that matter? So when you write j starting from 1 to n, it is still this x1 minus x bar ka square plus x2 minus x bar ka square and so on into the same thing. So these two are same thing, na? These two are same thing, na beta? So if you want to write it like this, x1 minus x bar ka square plus x2 minus x bar ka square and so on to xn minus x bar ka square whole upon this thing into this thing. Huh? Beta, I hope there is no confusion now. Huh? I hope there is no confusion. So you can just cancel one of them. Tuck, tuck. So you are left out with what? Just this guy. So this you can write as what? Summation of I starting from 1 to n xi minus x bar square. That is it. Beta, that is what summation of small ai square will look like. See, we will be using uh, these proofs somewhere in our other proofs. So that is the reason we are doing it this way. Third one, summation ai capital xi is equal to 1. Let us see how. Okay, now you look at this term. Summation of xi minus x bar ka square. I starting from 1 to n. Something like this. So how do you write this? Xi minus x bar into xi minus x bar. Fair enough. Okay. Which could be written as xi minus x bar into xi minus x bar will come out of the summation sign, it being a constant, into summation of xi minus x bar. Beta, what is this? Sum of deviations from mean. This is 0. So it will be like this only. I starting from 1 to n. I starting from 1 to n. Now you look at it in this particular fashion. Your AIXI. Hmm. AIXI. Beta, what was your AI? AI is what? Xi minus x bar upon summation xi minus x bar ka square. Beta, this is AI na? This is AI na? And if I multiply with an xi, it becomes like this. It becomes like this. Okay. I hope you understood what I'm saying. This is AI na? This is, and if I, okay, I use a different ink. If I multiply this with xi, it becomes this. This is AI, this guy, and I multiply with xi, I get this. Fair enough. Okay. What do you have? Beta, what is this? Summation of xi minus x bar into xi is what? This guy? Summation of xi minus x bar ka square upon summation of xi minus x bar ka square. Beta, that is equal to 1. So you have what? Summation of AIXI is equal to 1. We'll be using these in the different proofs. So you need to know the terminology well. Now you go back to your initial thing. What was in OLS estimator B2? What do you have written it as? Capital B2 summation of AIUI. This is what you have written. That's what you have written. I starting from 1 to n. So if you take the expectation of this is like this plus so these AIs are dependent only on xi, and xi's are fixed. They're non-stochastic. So even AIs are also fixed, non-stochastic. So AIs are non-stochastic, not AIUI. AI is non-stochastic. Given the assumption that x's are non-stochastic. But what is E of beta 2 is just beta 2, just a fixed number. AIs are constant, they'll come out of the expectation sign. Uh, E of ui. And what is E of ui? 0. That's your assumption. On an average, the error term is 0. So, what is it that you have proved? E of B2 is equal to beta 2. So, it means what? That the slope estimator of an OLS estimation, that is an unbiased estimator. So, slope estimator is an unbiased estimate. Right, beta? Chalo. Thank you very much.